Hello, it's Zach Kilpatrick. I'm your guest lecturer for today. We're going to talk about homogenization and averaging, in particular applied to traveling wave problem in the bistable equation. This is based on previous work by Jim Keener, but really building on decades of work on averaging and homogenization in spatiotemporal systems. Um, the first line of figures here you see is the typical time lapse of traveling wave propagation in something like the bistable equation, where you have uh, an invariant traveling front profile that simply moves to the right at some speed c. And the image on the top right is just a spatiotemporal plot where the warmer colors show the invasion of the front from left to right. If we add some heterogeneity to a system like this, for instance, making the diffusion coefficient in, say, a reaction diffusion model uh, periodically inhomogeneous, what you see, first of all, is that the trailing edge now has these periodic ripples on it. And in addition, the wave sort of lurches, so moves a bit faster when the diffusion's higher and slower when the diffusion's lower. And you can see these sort of ripples in the bottom right color plot in space-time. Well, one thing that's interesting is that the wave is still translation invariant up to discrete shifts. So if you shift by, let's say, t star, which would be the period of time that it takes to get through the spatial inhomogeneity, then the traveling front profile looks the same at those points. Okay, but in between, you have this sort of lurching behavior evidenced by the color plot. So there's a lot of things that you could describe in detail about wave propagation in these problems. We're going to tackle just one of those today, which is estimating the speed of the resulting wave, which is not exactly a traveling wave because it's not going to be translation invariant. But how the wave speed is slowed by the introduction of inhomogeneities. And we're going to use a homogenization technique, which is not just going to be classical averaging. We'll talk about why classical averaging might fail in this case. And this is all based on a paper by Jim Keener from the year 2000 in Physica D, looking at the impact of heterogeneity on nonlinear waves. And not only can heterogeneity slow waves, it can also just lead to pinning of waves, essentially where a front slows to a stop, and you just have sort of this standing front profile solution. So he works out on that in this paper. We're mostly going to look at the slowing problem. Okay, so this is all going to be built around the bistable equation, which you would have seen in partial differential equations. This is sort of a canonical model of traveling waves. You can do this sort of analysis for other systems that generate traveling waves, and I'll pose a homework problem for you where you actually look at this in an integral differential equation model of neural networks. And the basic idea is that you have a diffusion term on the right-hand side. We'll take its diffusion coefficient to be 1 for now. The nonlinearity needs to have 3 zeros in it. You could think of a cubic. You could also think of well, piecewise linear dynamics, as I'll take a look at near the end. But the main elements you need in this function f is that it has 3 zeros and that it's negative from 0 to alpha. This generates a system where waves will either have the 1 state, I guess, invade the 0 state, or the 0 state invades the 1 state. So depending on whether you have kind of rightward or leftward moving traveling waves in this case. Um, and I believe you may have worked out some exercises in PDEs to do this if you took graduate PDEs with me. So how do you derive these traveling wave solutions? Well, you make a traveling wave ansatz, which is to say that I'm going to look for solutions that are invariant with respect to this traveling wave coordinate or characteristic psi equals x minus ct. If you plug that assumption into this the PDE, you end up with just a second order nonlinear differential equation, which you can convert to a phase plane equation, and then apply some shooting methods in order to find effectively that solutions are going to have a form like this, where u as a function of psi is going to be some monotone decreasing function that connects an unstable fixed point in the phase plane to another unstable fixed point in the phase plane. So it connects two saddles together, and this is called a heteroclinic. It shoots from the one state to the zero state, and so in this case, if c is greater than 0, then you have that the up state, or u equals 1, invades the down state, u equals 0. As I said, this is a heteroclinic, which just means that it's a curve that connects two different fixed points in the phase plane. I mean, because of this, it's not structurally stable, which is actually one of the assumptions that you need to use sort of standard averaging. So we'll see, because of that, that we have to stretch beyond what's called the standard averaging theorem, which I'll introduce, and then we'll pivot and use something slightly different. So that's the homogeneous bistable equation wave problem. But what we're going to talk about is heterogeneity, or sometimes we might call this inhomogeneity. What is the effect of introducing inhomogeneity maybe into the diffusion coefficients, or the form of the nonlinearity? And biological and physical systems abound with these sorts of heterogeneities. It can happen because you have inhomogeneous porosity of media that you're studying. Maybe heat is conducted differently in different parts of the medium. Maybe electrical current is conducted differently. This sort of thing happens in networks of cardiac cells, which is really the motivation for Keener study. In that, if you model just a line of cardiac cells, the way that electrical current is propagated across the gap junctions or connections between cardiac cells is different than how it's conducted within a single cardiac cell. So the conductivity varies in this inhomogeneous way, and we want to ask how to model this. So there's a very general form that we can use for a periodic inhomogeneity of the diffusion coefficient of the bistable equation. And this particular form makes just the explicit analysis a little bit more amenable. You could take different forms, but the basic idea is that you're going to divide the baseline homogeneous diffusion coefficient by 1 plus g prime of x over epsilon, where g prime of x over epsilon is going to be some periodic function. Okay, represented here on the left is something like a sinusoid that is mean 0, and epsilon is small, as it always is, as you've probably encountered mostly in this class. And it's periodic, so then with a period of 2 pi epsilon. So the smaller epsilon is, the more rapid these oscillations go. And the idea is that this microscale is small enough that its effects can sort of be smoothed over when you look at grosser features of the model, like the approximate speed of waves. And so if epsilon becomes wider and wider, then that's going to start to break the general form of a standard traveling front, right? Because you no longer will have anything that even behaves to order 0, like just a traveling front. And so the idea is that this microscale is small enough that we can sort of approximate its effects by saying that we have a perturbed version of what we'd have in the limit as epsilon goes to 0. And as epsilon goes to 0, the oscillations become high enough that the effect is that you just recover the homogeneous system. Okay. So how do we handle this? Okay, we're gonna homogenize, basically average over this microscale somehow. And before we get to doing that for the traveling wave problem, let's just look at this simpler problem here, which would be just the steady state version of heat conduction in one dimension. So we've dropped the time derivative, we've dropped the reaction term, we just have steady state heat conduction. And the question is, what's the effect of this periodically varying diffusion coefficient? So our approach to start with is to separate what's called the macro scale, which would be things on the order of x, and the micro scale, which would be things that vary on the order of sigma here, x over epsilon. So as any small changes in x are going to have big changes on sigma. So sigma is going to detect these sort of small changes in your spatial variable. And even though these two are exactly related to each other, by pulling apart the micro and the macro scale, we can pull apart at orders of epsilon hierarchy the effects of the micro scale on the steady state, the features of the steady state solution. So in this case, if you take the total derivative now of x, it involves both 1 over epsilon times the partial with respect to sigma plus the partial with respect to y. So if we apply this then to our steady state problem, we have this much more complicated form of our derivative with respect to x, and then the diffusion coefficient times the derivative with respect to x again. And it's separated out into this term that's a derivative with respect to x and a derivative with respect to y. So what are we going to do with this? We're going to say, well, let's assume now that the effects of the microscale can be separated into a hierarchy of epsilon contributions to the solution u of x sigma now. And at 0th order, we'll say that the microscale has no effect. Okay? And at order epsilon, we'll say that the microscale does have an effect, and so on at order epsilon squared. Okay? So that's a strong assumption that the microscale does not impact U0, and we'll explore sort of breaking that when we looked at the traveling wave problem. The other thing is that because we assume that G prime has 0 mean, we're also going to assume that U1 and U2 have 0 mean as well. Okay, so this sort of 0 mean perturbation is going to result in a 0 mean perturbation to the solution. Okay, and also because G prime and G are periodic and sigma, so are U1 and U2. Okay. So as I said, we are going to need to consider the microscale at 0th order once we go to the traveling wave problem, and we'll see the effect of not doing that now in the case of the steady state heat conduction problem. Okay, so this is just the now the partial differential equation and the perturbation expansion that I wrote down on the previous slide. If we expand now in order epsilon, to lowest order of epsilon, we actually have terms of order epsilon to the minus 1/2, right? Because you see here you have a 1 minus epsilon and a 1 minus epsilon, so you have these terms that are products of 1 over epsilon. Sorry, 1 over epsilon times 1 over epsilon. Okay, so what remains there is this equation here. Okay, and at order epsilon to the minus 1, we have this more complicated equation regarding all the cross terms in our partial differential equation up in the top left. Okay, so let's treat the order epsilon to the minus 2 equation first. Okay, if we just integrate that with respect to sigma, Then the right-hand side would generate just a function of y, because if I'm integrating with respect to sigma, then things just involving a function of y, if I differentiate it again, those would go away. That becomes a fairly simple sort of first order partial differential equation, one that you might think, well, maybe I could even solve that using something like method of characteristics. We can, in fact, sort of solve it by hand using the assumptions that we've already taken on. And it involves both a u1 and u0, okay? Both of which, so far, we don't know. K of y is just some unknown function. G prime we actually know, okay? Well, first of all, we know that U0 is supposed to represent the average behavior. So what we would get by integrating out our solution over space, okay? And U1 and du1 dy have zero mean. So if we integrate that above equation over the period of the inhomogeneity, okay, then du1 d sigma should integrate to 0 because it has 0 mean. Du0 dy will not because it's not necessarily 0 mean over the period of the microstructure. Okay, and also we know that g prime of sigma has 0 mean. So if we integrate that over the period of the inhomogeneity, then it should vanish. Okay, so when we do that, we just have this equation k of y equals du0 dy. Okay, if we plug that into the PDE that we started with, right up there, then we end up with du1 d sigma plus du0 dy. This is equal to du0 dy. So now we've replaced k of y with du0 dy. And we still have our 1 plus g prime of sigma. So when we simplify this PDE now we just have a relationship between u1 and u0 through g of sigma. So we've just integrated up with respect to sigma once, and we end up with this fairly compact expression for u1 in terms of u0. Okay, so if we plug this into our second equation, okay, we still don't have a solution in terms of u0, but we can say something about what our solution will look like. So now I'm just plugging in this expression that we derived from the first equation into our big long second equation, and things collapse down nicely. Okay, so we still have this du2 d sigma term, but now we've replaced all our du1 dy and du1 d sigma terms using the expression that we derived for u1. Okay, and canceled some things out, and we can say that this is equal to 0. Okay, now if we average this equation, again, anything that depends on sigma should average to 0. Okay, because everything on the order of the microstructure averages to 0 over sort of long wavelengths. Okay, so the periodicity of G prime, U2 all implies that if I integrate this, I end up with the first two terms are going to vanish because they involve G of sigma and U2 of sigma. And the only thing that is not going to be periodic, okay, when we average over overall space, is going to be the d2u0 dy part. Okay, so this is now our homogenized equation. Okay, which we could solve. It's just a second order equation for u0. Okay, and we would get a pretty boring solution in this case. And so the point is that if we take this approach now, the heterogeneity is going to have no effect on the mean field. Okay, So this whole exercise was basically to demonstrate to us that um, if we have periodic inhomogeneities and we just sort of try and average them out directly, then we're going to miss something. We're going to miss something about the impact that periodic diffusion has on the dynamics of our solution. Okay, we're not even really looking at dynamics in this case. Um, but basically this tells us that at the level of the mean field, okay, averaging will sort of shroud the effects of periodic diffusion. Okay, so if we want to do things like augment the traveling wave speed and the traveling wave problem, what we have to do is alter this method in order to make it work well for the full bistable equation within homogeneity. Okay. But one thing that I will note is that if we go back to the previous slide, what we find is that the I think I can get a pointer here. Can I get a pointer? What we find is that the U1 expression that we have really suggests a specific form for our perturbation expansion. So if we go to what now we would suggest as the form of our perturbation expansion, we see that it should involve something like our periodic inhomogeneity multiplied by the partial derivative of u0 with respect to the microscale. Okay, so this we got through that one step of averaging. So we will use one result from averaging in our perturbation expansion, okay? But we won't average everything out in terms of the primary PDE, okay? So what would we want to look for in terms of the effects of heterogeneity on the solutions to the PDE? One effect could be that in a limit of very strong heterogeneity, we don't have any propagation at all, but waves get pinned in place, okay? And Keener goes through that analysis, okay? And I have some handwritten notes on that I can send as well, but we'll not cover that here. I really want to focus on, in the limit of sort of weaker heterogeneity, how this heterogeneity can slow the velocity of waves, okay? And actually compute this correction. So let's go back to our original inhomogeneous bistable equation. Again, our diffusion coefficient is going to involve 1 over 1 plus this periodic inhomogeneity. Okay, what are our initial conditions? In this case, it turns out they don't really matter that much. Okay, because for any initial conditions, eventually, if this traveling wave-like solution is attracting, then the dynamics will approach that. Okay, and we're just assuming that that's what's going to happen, although I'm not going to prove that to you. What are the relevant boundary conditions? Well, really, we have sort of free boundaries, but we can just make an assumption that the spatial derivatives of u approach 0 as we go out towards infinity. Okay, so in uh, in the limit of small inhomogeneities. Okay, so we could try applying the averaging theorem to this, and there's a nice book by Jim Keener called Principles of Applied Math where he writes this out. I'll just sort of copy that here. And the classical averaging theorem says that if I have some differential equation of the following form, okay, I'm just going to take a first order nonlinear differential equation to demonstrate this point. You can generalize this to PDEs. And it involves some nonlinear function of u, some function of x on the microscale, and maybe some function of epsilon, and epsilon is small. There is some change of variables where you can take u and re-express it as y plus epsilon times some function of y, where y is a function of x, and x on the microscale and epsilon. And you can rewrite that ODE as this first order average system, okay, which is what we did on the previous slides, where f of 0 is just basically what happens when you average out over the microscale, specifically when you average over the microscale. Okay. Now, this only is going to work if our system or solutions are structurally stable, which we said at the beginning our traveling fronts are not. They're heteroclinics between two saddles, and so they're very fragile. And so the phase plane is not structurally stable, or the solutions that we're interested in. So we're going to forego sort of doing this sort of standard averaging approach that I went through with the steady state heat equation, and we'll just examine the full problem, okay, not just this reduced problem that we've written down now. And so we'll start by rewriting the full partial differential equation up here, okay, as the following system. So what am I doing here? Really, I'm just taking f. I'm moving it over to the left side, and I'm flipping the sides so that we just have our diffusion term here on the left is equal to u sub t minus f of u. Okay. But if I say that, well, let's just express u sub x, okay, uh, we'll express a new variable v in terms of u sub x. V times 1 plus g prime of x over epsilon equals u sub x. So then if I differentiate v, that's the same as differentiating u sub x divided by 1 plus g prime of x over epsilon. Okay, and then that will be equal to ut equals f of u. Okay. So I'm just sort of taking a page out of the book of sort of converting second order systems to phase plane systems, but doing it for this PDE system. Okay, so this will just make our calculations a little bit smoother. And remember I said our previous calculation suggests that up to order epsilon, we should expand u in terms of some function y plus epsilon v times g of x over epsilon. Okay, so let's plug this perturbation expansion here now into our rewritten system of PDEs here, and we get that y sub x now is equal to v minus epsilon v sub x, g of x minus epsilon, x over epsilon. And we have an equation v sub x equals y sub t now. We have this partial derivative plus epsilon v t, g of x over epsilon, minus now the nonlinearity f. Okay? So we're ignoring terms of order epsilon squared and above. And now we're just going to handle this system. Okay? So we've done a bit of perturbation theory already by introducing this small parameter. Okay, we're going to now make a key assumption, which will be important for estimating our wave speed, as it depends on the inhomogeneity. Specifically, we're going to say that, recall the standard traveling wave coordinate for a traveling wave solution would be x minus ct. Okay, but the important thing here is that the inhomogeneity is sort of sometimes going to slow down the wave and sometimes going to speed it up. Okay, if you're in the patch where the diffusion coefficient is lower, the wave may go slower. If you're in a patch where the diffusion coefficient is higher, the wave may go faster. Okay, and specifically I mean where the leading edge of that traveling wave is. Okay, so it's going to sort of speed up, slow down, speed up, slow down. So we need to be able to track that, and we do that using this function phi of t. Okay, so our new traveling wave coordinate now is going to sort of absorb this time-dependent function phi of t. Okay, And so if we plug that into our phase planish looking system from the last page, we have this equation here for y and this equation for v. And in particular, we're going to seek perturbative solutions, okay? So it may now look like I've sort of averaged out the effects of the inhomogeneity, but hidden now in this traveling wave coordinate psi is the effect of the inhomogeneity in the form of this function phi of t. So the main player in this game that we want to try and uncover is phi of t. What is phi of t? We need some sort of method for extracting what phi of t is. Okay, we really only want to find out some scalar quantities about these solutions. We don't necessarily want to solve for the full form and shape of these perturbed traveling front solutions. We just want to know how much the front is slowed down or sped up by inhomogeneities. Okay, so now psi is sort of absorbing these effects. So we have managed to sort of sneak in the effects of these inhomogeneities to our zeroth order terms here, y0 and v0. And then at order epsilon, we have this y1 and v1, which we don't really want to solve for, but we want to sort of use them in order to uncover what phi of t is. And phi of t, what's phi of t? Well, to zeroth order, its derivative is going to be c, because it would be like ct. And to order epsilon, we're going to have some function phi 1 prime of t. Okay, and then we don't really care about over order epsilon squared. We could go to higher order, but most of the interesting conclusions are going to happen at order epsilon. Okay, so what happens to the zeroth order equations? Well, we just recover the standard traveling wave solution, okay, as well we should. And we know how to solve that. We solved that on the second slide of this talk. You can look back for that. It's just going to be some traveling front solution that's going to have some shape UC of psi. So it's going to be, like monotone decreasing in psi. It's going to go from 1 down to 0, and v0 is just its derivative. Okay. Now, first order, we have this equation for y1 and v1 that involves these inhomogeneous right-hand sides. Okay. And I guess if you've managed to get through 2/3 of an asymptotics course, I would hope that one thing that eventually pops into your mind is that this is set up well to apply Fredholm alternative, right? We have something that we know what it is on the right-hand sides of these equations. We know all of the things on the right-hand sides of the equations, okay? And well, up to, I guess, phi, but we know everything else on the right-hand sides. And we have a linear operator on the left-hand sides, right? Linear operator in y1 and v1, okay? So Fredholm alternative, we want to apply the Fredholm alternative. What does that tell us? It tells us basically to ensure a bounded solution, okay, to this first order equation, we should require that the null space of the adjoint of the linear operator, okay, defining the left-hand side, should be orthogonal to the right-hand side of this equation, Fredholm alternative. That's how we sort of climb this hierarchy of order epsilon equations. Okay, well, we only need to climb one rung. It'll just be the order epsilon equations. Okay, what's our adjoint system? Well, you take the adjoint of the linear operator. You can see here that you have a minus v1 here that shows up as this -1 term here. We have a f prime y of 0 here that shows up as a f prime y of 0 over here. Okay, the minuses that would be in front of all this go away if you do the integration by parts to get the adjoint. And the on diagonal terms are 0 and c here. Okay, so this is our adjoint. It turns out you can figure out what f prime of y0 is just by looking at the v0 equation, rearranging things, and plugging in what v0 is. Okay, and then the v1 star equation is not hard. Okay, and it turns out you can work this out on your own. It may be tucked into the Keener paper somewhere. that the null space of this adjoint equation is e to the c xi, okay, times the vector minus uc prime prime uc prime. Okay, so that's explicitly calculable. That's nice. Okay. So, we just have to apply Fredholm alternative, essentially take this null space and take its inner product with the right-hand sides of these equations, okay? So this pairs up with this, okay? And we can figure out what V0 prime is. It's just this here, okay? And we take this, e to the c xi u c prime. We take the product of that with this, and then we sum these together, okay? And if we move the phi 1 prime of t term over to the left-hand side of that equation, saying that dot product or inner product is 0, then we end up with the following longish equation for phi 1 prime of t, which is the only thing that we don't know in the system up to phi, okay? So we can simplify this a bit, basically by noticing that the product rule allows us to make this set of terms a little bit more compact. Okay, and then if we integrate that right-hand side by parts, and we isolate the phi 1 prime, or just to order epsilon, we can call that just phi prime. Then at order epsilon, we have d phi dt equals c minus now this function, okay, which we'll call capital phi, okay? So this is still non-trivial. It's actually a non-linear differential equation for phi, because you see phi is tucked up in here. But I will show you an example where we can explicitly solve this in the case of piecewise linear dynamics. Okay, so at this point, yeah, you still have something that maybe you would have to solve numerically, but it's way simpler than coding up, some sort of finite element in order to find out your solution to that full nonlinear PDE system. And we get some insight here into what happens with the speed of the wave. In particular, if this function phi, capital Phi, okay, ever has amplitude above c, you should expect pinning of your wave, or you should roughly predict pinning, because if phi d phi dt becomes 0, then you stop. You get to this fixed point. Okay, so if capital Phi is large enough, propagation failure occurs. Okay, but in order to really take a closer look at this equation that we've derived, let's look at a calculable case. Okay, I want to also note that this is a fairly simple equation that we've managed to extract from a longish, a set of calculations, and again, everything in this function phi, except for little phi, we can compute, or we have access to computing. Okay, one way or another. Okay. So let's look at a case where we get actually a fairly clean solution, the case of piecewise linear dynamics. So you might say, well, that's has issues of continuity, but we can compute all our solutions explicitly in this case. Okay. So in the case of piecewise linear dynamics, our nonlinearity is just going to have a step right here. Okay. So that we have a 0 at 0, we have a 0 at 1, and then we sort of have this 0 at alpha. Okay, but we just have a discontinuity that really is going to behave like a 0 as far as we're concerned. And it's not hard, actually, to explicitly derive solutions to the traveling wave equation. Again, you should have worked this out in exercises in the PDE course. There are related ways of doing this, I think, sort of laid out in exercises in Michael Shearer's book. And the idea is that your traveling front solution is going to have some just exponential decaying term for psi greater than 0, and some exponentially saturating term for psi less than 0. And you can work out those eigenvalues because you just have the piecewise linear equation when you go to the phase plane. Okay, and note that if you require continuity of the derivative across psi equals 0, this is going to give you an implicit equation for the wave speed c. Okay, so if we plug in lambda plus and lambda minus, okay, we get this sort of longish rational equation. Okay, we can cancel some things out, and we get an implicit equation for c in terms of alpha. Okay, but we can rearrange things again, and we end up with just a quadratic equation that we can solve for c in terms of alpha. Okay, so you see here, if alpha is a half, then the wave speed slows to 0. Okay, if alpha goes to 0, the wave speed diverges to infinity. Okay, and for c sort of between 0 and a half, you have forward moving waves of speed between 0 and infinity. Okay. And so this means that this little term here on the bottom, okay, we can solve for straightforwardly. We get this very compact expression for the denominator of the capital phi formula. Okay. And now let's take a specific function for g. Let's take the function g prime of x equals just a sinusoid. Okay, so we have sinusoidal variation in the diffusion coefficient. If we plug that into our expression for the integral in the numerator of capital phi, we can compute that integral, and we get actually some terms involving epsilon squared, but we really only want to preserve the ones at order epsilon. So to order epsilon, actually, we end up with an extremely compact expression, okay, which just ends up being d phi dt equals c plus, and now this is our capital phi. It's just epsilon a over 2 cosine of phi over epsilon. So what does that tell us? It tells us that for as we move along, okay, in phi, so for some values of phi, the speed of the wave is actually going to be faster than c. For other values of phi, where cosine is negative, the speed of the wave is going to be less than c. Okay, and in particular, if epsilon a over 2, the amplitude of this sort of modulator of our instantaneous wave speed, gets to be greater than c, then we get pinning. So we basically, in that limit, phi eventually will hit a fixed point, and the wave will just get stuck. Okay. So as long as phi prime is greater than 0, though, we can actually average this to get an average wave speed. So now the only other sort of piece of averaging that we've done in this equation is to say, well, as long as this right-hand side is always positive, the wave or wave-like structure is going to continue to move along. Let's find out what its average speed is over a period of the microstructure. Okay, 2 pi over epsilon. How long does it take for it to move 2 pi epsilon? Okay, we integrate over phi from 0 to 2 pi over epsilon, 2 pi epsilon, excuse me. Just using a sort of separation of variables of our nonlinear differential equation. This is a computable integral, which gives us 2 pi epsilon over square root of c squared minus epsilon squared a squared over 4. So then the average speed, the ratio between the average speed and c is this, 1 minus epsilon a over 2c whole thing squared. So that means that even though the wave speeds up and slows down, it turns out that the net effect of the heterogeneity is to slow down the wave, okay, over time. So that means that as we increase the amplitude of the heterogeneity, okay, then as the heterogeneity gets stronger and stronger and stronger, or the microstructure gets wider and wider and wider, this is eventually going to reduce, okay, the average speed of the wave and will eventually cause the wave to fail. Okay, the wave will no longer continue to propagate. It's not going to die. It's just going to sort of freeze in place and not propagate. Okay, and so it turns out you can calculate this nicely for other examples, such as the cubic nonlinearity. The formulas are not quite as clean as piecewise linear dynamics, but Keener goes through them in that paper. Okay, and just to conclude now, what have we showed? Well, that really just direct averaging that ignores the fact that heterogeneity is going to modulate the wave speed will not properly reveal the effects of inhomogeneities on the propagation of waves. So what we had to do was actually to incorporate the effects of heterogeneity into the wave characteristic itself. Okay, so we had to express sort of the traveling wave coordinate in terms of this non-trivial function phi of t, which we solved for using the order epsilon hierarchy and the Fredholm alternative. Okay, and our perturbative equations give us this nice rough estimate for wave pinning, as well as sort of how much increasing the amplitude or the micro scale of the heterogeneity will slow down the wave. And typically it's always going to slow down the wave in this case. Okay, so I'm giving Mark a short homework exercise where you can sort of explore working through this in another system, and you can even push on and compute things explicitly in that case as well. And I'll give you another paper by Paul Bresloff that goes through that. But that's it for asymptotics of traveling waves in homogeneous media. Thank you.